In this video, we want to use Python to perform some analysis of experimental data. The data is magnetic field data. The magnetic field we've measured using a smartphone and an app called Phiphox. The smartphone gives us three different components of the magnetic field from some magnet. And we move the magnet closer or farther away from the phone and we record the corresponding magnetic field strength. Using the app, we've also carried out a number of repeats. We've used what's called a time run, where we've run the measurements for 10 seconds, accumulating almost 1,000 repeat measurements during that time. So for each distance, we've measured many repeats. And what we want to do, we want to average those repeats and calculate what the mean magnetic field was at different distances and what the corresponding error on that mean is. In a subsequent video, I'm going to show you how we then use the mean and the error to calculate the key parameters of interest, which are the magnetic field moment, or the source of the magnetic field, and this power n, how quickly does the magnetic field decrease with distance or. So we've already got this data, and I'm going to do the analysis in Python, and I'm going to run the Python code on a web platform called Cocalc. So this is a free website that you can use to run programming languages, including Python. And it provides an easy way to show you how we can construct a simple program to perform this statistical analysis. Let's start by transferring our data into our folder. So as I said earlier, I'm working in Cocalc, so I'm working on this online programming website. My data is stored on my computer, so I want to transfer my data to this working folder on Cocalc, where I'll do my analysis. So I'm going to go to my computer window, which is off screen here, and I'm going to transfer a folder called magnet data, and I'm just going to drag it into this drop zone here, and then this will start to upload the folder into Cocalc. Great. So the main folder I'm working in is called magnetic field analysis. I've dragged in my data. The data is from a magnet, a cylindrical magnet, and one point I should make later in my analysis is to adjust the distances in my data, and I'll take you through that later on. So let's have a quick look at one of these data files, and this one here is 1 centimeter, and this data was recorded using a smartphone's magnetometer, and the data was recorded over a time series. So the smartphone took repeat measurements, it looks like from 0 to around 10 seconds. So on the left hand column we've got time, so these are all the different repeats. What we're interested in is the magnetic field in the x direction, and that's being measured in microtesla. So we've measured our magnet, and we've measured it as a function of distance along the x-axis. So this second column here is the column of interest. So we'll be working in microteslas, and we can convert it to teslas later on. But for the moment, I just want to see what I need to load in. Now, obviously, when I load in this data, I want to maybe ignore this header file, and I'll show you how to do that. Firstly, let's make up our Python script. So we've got the data; it's all in there. I want to make an analysis program to do it. Now, you can write your analysis in script in a Python file, but for this demonstration, it may be easier to use a Jupyter notebook. So we'll call it the first part of our analysis. The first part of our analysis will be to get the mean of the repeat data. So I'm going to call it mean repeat data. And after writing the file name, I'll just click on Jupyter Notebook, and here we go. So this notebook file will be in this same folder as the data. So somewhere down there we can find that it is there in this data directory. So we'll go back to our empty notebook. And as always, when you're writing a program, don't dive straight into writing a complete program. Take it in steps. And the first step I want to try out is, can I remember how to load in data? And for much of our analysis, we will be working using a Python module called NumPy. So I'm going to import that module, NumPy. So we got import NumPy. NumPy stands for numerical Python, and it's the go-to kind of library or module. It's got all these amazing functions in it that lets us do all the analysis that we typically want to do on our data. So import NumPy. I'm going to call NumPy NP for short. And I may also want to visualize my data when I get it imported and averaged out. So I'm also going to import matplotlib. And matplotlib, as the name suggests, is the plotting library, or the plotting module. So matplotlib, and it's a submodule called pyplot. And instead of using that long name all the time, I'm going to just shorten it to PLT. Okay, so let's run that. And no errors, good. So they're the real names. And I want to start testing out how to load in my data. So if I make a variable to store my data in, I'll call it just simply data. And I'm going to load it via NumPy's load text. So NumPy's load text takes the main argument is the name of the file. And let's start with this file up here that we looked at earlier on. It's 1 centimeter .csv, and I need to make a string. What I could do is put the file name straight in here. So 1 space centimeter .csv. And notice that CSV stands for comma separated values. Yeah, so I can tell load text to anticipate these commas, and these are referred to as delimiters. So I can specify the delimiter as this option here. Delimiter equals a comma. Now, as soon as I do this, we can test it and see what happens. And we've got an error here that says that the interpreter couldn't convert a string to a float. So you can see here, it thinks this needs to be a number. And what it's trying to read in initially is this header line. There's two ways around it. I could put a hash symbol here, and that will tell the interpreter to ignore this line. Or if I've got too many files to do that manually, I can simply go into my load text command again and put another option called skip rows. I can just ask it to skip the first row. So skip rows equals 1, so skip the first row, and now no error. What I'm going to do, I'm going to make a second cell here. This is my kind of testing cell. I just want to test that my program is developing and I'm reading in things that are correct. So the first thing I want to test is, what does my data look like? And since we're in a Jupyter Notebook, we can just write it and press return, and that will print out the values. So we got a big array. It's showing us a little sample of that array, and it's got lots of numbers. That's good. I can also check how big my array is by typing whos, and it says one of the variables I've got loaded in is this array called data. It's got 5 columns and 984 rows. And if we go down to the end here, just off screen, I've got around 985 rows. So that's over almost 1,000 repeat measurements, which is fantastic. So that's the power of using your smartphone or any computer indeed to record data. You can do it very, very effectively in getting lots of repeat values for you. And okay, so that's just my diagnostic cell. I'm just going to leave that there, and I'm going to start completing my program. So I've got the data, and the data I'm interested in is, I guess, this X component, and this is the second column. Okay, so what I could do is go b field is equal to data, and the second column I use an index, and the index is to say select a certain row or select a certain column. I want to select all of the rows, and this is this little colon symbol. All of the rows kind of comes first, comma, and then the column comes next. And I want to say the second column. Now column numbers in Python starts from 0, so the second column will be column 1 in this case. So you got to imagine that the time column is column 0, and then this column of interest here is column 1, and this will be column 2, and so on. So I'm selecting my data, I'm slicing this array, and I'm going to save the X component to a new variable called bfield. Okay, so let's run that and see that we get an error. Good, and my who's now tells me that I've got bfield, which is just a single column of all my X component values. Okay. Now, if I want to get the mean, I can make a new variable called mean, and numpy's got all of the functions for mean and standard deviation, etc. So we can use numpy.mean to calculate the mean of all those repeat values. Great. And now that should be also stored in memory. So mean is there, and the mean value is 1,305 microteslas. Okay. So the idea with this first program is to calculate the mean of all these repeat values for each data file, and each data file is a separate kind of distance away from my detector. So the magnet here in the first case was 1 centimeter away from the detector, and I think we probably go from 1 centimeter all the way to 27 centimeters. So we've got roughly 27 files. So we want to do it for each file. And we'll do that using a loop a little bit later. But first, besides the mean, I also want to get the statistical error on the mean. And the statistical error uses the standard deviation. So the standard deviation is available via NumPy again. So it's called STD. And we'll get the standard deviation of these repeat values that we had for the X component. Now, once you have the standard deviation, you divide it by the square root of the number of values, and that's how you get the error on the mean. So the number of values you can easily get from Python by saying, what is the length of the bfield array? And the bfield array, we discovered, has a length of around 984. So there's 984 values in there. So this length function will tell Python that. So we'll have the square root here of 984, and that will give us the error on the mean. So let's run that. No problems, great. And again, that new value of error is 0.011. Fantastic. So it's quite a small error on the mean. If the value is over 1,000, and this is 0.01, so it's a fraction of 1%. So very, very small statistical errors on these repeats, which is really good. I mean, that is really helped by the fact that we've got 1,000 here, or the square root of 1,000. And so that will be a nice way of minimizing the overall error, because we're dividing by the square root of 1,000 there. Okay, so that's the main idea that we want to do for each data file. And then we want to store all of these values for the mean and the error in another data file that we'll use in our final analysis later on. Now you can see if I was to do this manually for each data file, that'd be 27 times. I can do it a little bit faster if I put this in a loop. Okay? So what I'm going to do is I'm going to leave this code here. This is my working code for one data file. And I can make a new program here that will do it for all of them. And we'll use this as a little template. Okay? So let's, again, start writing our new program here. We're going to import the modules as before. And we want to, I guess, somehow make a for loop. And a for loop is a way of doing something again and again and again a certain number of times. And because we want to do this 27 times for the 27 data files, we'll have a loop that goes up to 27. So yeah, so we want to make it we want to first I guess build our for loop. So let's go for I, and I is the counter. I will go in range, we'll try up to 28, just in case range only goes up to the value -1. So this should go up to 27. So from I in range 28, hopefully will give us I equals from 0 to 27. And just to prove it to ourselves, let's just print I, just to prove that we understand how this works. So I will go from 0 all the way to 27. Fantastic. Okay, so that's correct. Now, so the thing that changes is this name of the file. Yeah. So the name of the file will change from 1 to 27. So I want a feature here that will do that for me. So, so the only thing that changes is this first part. So what we could do is we can make a variable called file or file name. And it will be, I guess, the value of I plus this remainder of the string. So we're going to have a string here. And so we're going to add a space followed by the centimeter.csv. We're going to add that onto this I. And if I is a number, we also want to make that a string. So str makes I a string. So you can change numbers into strings. And a string, remember, is just characters. Letters and numbers can be represented as a string of characters rather than a number. And to check again that we're doing this right, let's put another diagnostic print statement in here for file, and hopefully that will show us that the file names are being formatted correctly. So here we go. We got 0 all the way to 27 centimeters.csv. Now that we know that the file name is going to change correctly, we can then start loading the data. And we'll copy this load text line that we used earlier. So that showed us that this worked. Now instead of the file name here in the string, we'll just use a variable called file, and that will substitute in the string that we will make in here for load text to load. Everything else stays the same. And then we can start getting our data and the error. So again, we'll copy and paste this. And we'll make sure that these are all indented. So I'm just pressing the tab button on near the top left of the keyboard to indent those two lines. Great. So we'll load the data. We'll calculate the we'll, I guess, extract the X component of the B field from that data. We'll get the mean of that, and we'll get the error on the mean. Let's just see if this runs without any main errors. Okay, we've got an error. The error I'm seeing at the bottom of the screen, just off this video screen, is that the 0cm.csv is not found. So it's not able to find the file name. I is going from 0 to 27, but our file names begin at 1, not 0. So what we could do is, rather than 0 to 28, we can go from 1 to 28. A way to do that is with numpy's arrange function. We can make an array arranged from 1 to 28. And let's see, will that work? Brilliant. Now, just to prove it to us, I mean, we'll just get rid of this line for a second. We'll print the file name again. And yes, it's starting at 1. Great. And it's finishing at 27. Brilliant. Okay, so we fixed that problem, and let's go and get the data now. Let's copy and paste what we've tested out before, and select that, press tab, remove this empty line. Now we've got data is load text. We'll give it the file string that we've made there. Everything's loaded in, get the mean. Let's see if this runs without any errors. Great, no errors, brilliant. So what it's doing here at the moment is that, and I'll just show you by typing who's to show you who's in memory. You'll see that it's going to make an array called b field, mean and error. And the mean here and the error, single values. So what it's doing is it's getting the mean of the x component for each file and the error. But then on the next loop, it's going to overwrite them. So we want to make sure that we don't overwrite these values, because we want to keep the mean and error for each file. We don't want to overwrite it. So a way to do it is to store these values inside an array. We need to make those arrays before the loop starts. So we want to know how many values we need. And a way to do it is to, I guess, define how many files we have. Now we've done that here. So what we could do is say this distance variable that the file names are named under, will go from 1 to 28 centimeters. The number of files we're going to read will be the length of this distance array. So 27 in other words. And then we can use that to build up empty arrays full of numpy.zeros. So numpy.zeros will help us make an array, I guess 27 spaces or 27 element array full of zeros, and then we can overwrite those zeros in here. We can say if I is going to go in range from 1 to 28, then we can say if this mean array already exists, yeah. And I can show you what this looks like. So if I just make a test cell here, and then we can say what is mean, it will say just full of zeros. So we've got an array of 27 elements. They're all set to 0 initially, and then we're going to overwrite those zeros at each step in the loop. So when the loop is at 1, this will have to start at 0. So I minus 1. So if I is starting at 1, my array has to start at 0, of course. And likewise for this guy. So we're going to make another array for the error. So error is equal to the same initialization. So we're going to initialize an empty array of zeros for that. And hopefully this works. Great. So now let's look at the mean array. It's full of all of the values that we've got. Now we did this earlier for the first value for 1 centimeter, and let's just check that these things are consistent. So the mean of the first that we did was 1305, and this is now, if you factor in the 1000 here, is 1305. Great. So this loop now has automated the process that we did earlier for all 27 files. So this is why we did the loop. You could of course just do the initial process that we did for one file. You could do that 27 times yourself manually by copying the code, but it's not very efficient. I know the loop looks a little bit more complicated, but if you want, both options are available to you. The efficient one or the long-winded copy and paste one. Likewise, the error array should be full up of values. They're all very small, which is very reassuring. Again, because we took so many values, repeat values. So that's good. So now the final stage is to save we want to save mean and error, and also I guess distance. So to save it, we have numpy.saveText. So numpy.saveText is the companion to load text. So load text takes it in, save text saves it to your computer. Now the save text, so we're going to give it a name. So we'll call it mean data, and we'll use a text file, basic text file for this. Now we want to save the distance in centimeters, the mean and error on the mean, they'll be in microtesla. And we want to save them in this text file. I like to save them as columns, and to do that in Python you use numpy.c for column, and then there's an underscore here to ensure that it's written correctly. Now, so let's run that. I don't need these cells anymore, so I'll just delete them. Numpy.save, don't want to use that. I want to use save as text, and we'll overwrite the file that we had there before. So mean data, let's give that a go. look in the files now. Mean data. And yes, we now have the mean data. I always like to maybe add a header. So a header line will tell the user what's in those columns. So before that, let's define a header. Now a header is just a string. Maybe I'll call this variable info. And I want to say that the first column is distance in centimeters. And the second column is B field in microtesla. And the last column is the error in microtesla. Now I can tell save text and use it by putting in this header option. Header is equal to the string I've called info. Run that. Check my data file, and indeed the header has been added. Great. So this is the data. I've got mean here, or in the middle, I guess. The mean B field is this second column, and the error on the mean is there, and the distances are on the left. So the second video we'll do on this is to show you how you perform your analysis. The analysis, just to kind of give you an indication of what we want to do later, is to have a look at how we can perform a fit onto the data. So if I look at the raw data of this mean, so we've got D, mean, and let's see what that looks like. So rather than just straight line or join the dots, I will put points so we can see what it looks like. So you can see that we've got some kind of distribution of our data, and we can, in a further video, show you how you perform what's called a chi-squared analysis. So we can do a regression analysis and fit some function to this data.